welcome back to the channel. It's been quite a while since I put a video out, and that's just because I've been busy with other things in life, and in my free time I have been working on my current project, which is just about finished, and I'm hoping to continue on in this series of videos and present that project to you. This video, like I said, is going to sort of kick off this series. I'm going to talk about some basic stuff, to kind of set the talk about some concepts and things to set in place for the next parts, probably a two-part series on my project. So ever since I did the video a few years back on the HP334A distortion analyzer, I've kind of been focused on distortion analyzers and signal sources. At the time, I didn't have a very good source to fully test the 334A distortion analyzer, and so that sort of kicked off a little bit of looking deeper into the subject of low distortion signal sources and trying to find a signal source for that, and then it just sort of went from there. And so that's to kind of hint to lead into my project, and to kind of go where I want with this. I want to talk about distortion analyzers for a little bit, and what I want to do is sort of walk through the how a distortion analyzer works. We'll go through the basically the building blocks of what makes up a distortion analyzer and how they can take that signal and produce an indication of signal distortion. Now, I've looked at many of the manuals for the common distortion analyzers that are out there. Obviously, the HP334A service manual, spent quite a bit of time on that one with the repair on that unit. And since then, I've also acquired an HP339A distortion measurement set, which I think I used in my previous video. And that unit works fine, and it's got a little bit better performance than the HP334A distortion analyzer. It also has the source, which makes it a complete distortion measurement set. But I've also studied some of the other manuals for the other units on the market. Tektronix has a few distortion measurement sets, the AA501 and the DM4804, I believe is the number. There's a Cronheit model out there, several by HP. Already mentioned the 334A and the 339A, also the 8903. And there's at least one, I think it's a 4443 distortion measurement set. So look, I've read through those manuals. Also, Cronheit, I think I mentioned that one already. And Heathkit actually has a distortion analyzer set too that's based on the HP334A. It's actually it looks like almost a clone of the HP334A. And I believe there was a licensing agreement between Heathkit and HP when they did that unit, and I think the Heathkit, from what I read, the Heathkit had to limit its performance, so they limited the range down to the lowest range on that one is 0.3%, so that would give you minus 50 dB of fundamental rejection on that unit. So I think that was part of the agreement there for that. But if you look at the build on the Heathkit unit, it's essentially a clone of the HP334A, even going so far as to use the photo resistive assembly like the HP334A uses. So looking at all those manuals, reading through all those, studying how the topology, how they work, they essentially all come down to the same sort of building blocks. And that's what we're going to get into here, because like I said, this is going to set the groundwork for the project that I've been working on for the last 2 years. I believe I started this project back in the fall of 2022, So it's been that long as I've been working on this project. It's been quite a consuming project. Had a couple of slowdowns along the way. Mainly the my spectrum analyzer failure, which we saw the videos on that. But I think it's finally at the point where it's in the finishing stages, and then I can present that to you. I don't want to. I want to get it done and present. I'm really ready at this point to move on to other projects, and I've got other equipment that's been piling up in the lab down here that needs to be tended to also. So we're going to get this series going. We're going to get that project presented, and we'll walk through it in the parts 2 and 3, and then we'll move on from there. So let's get started here. All right, distortion analyzer building blocks, or major portions of what would make up a distortion analyzer set. Let's start with our test signal. So we're going to have some sort of test signal that we're going to have to put in to our distortion measurement set. And this can be some sort of oscillator. It could be an external signal source, or it may be, say, like in the case of the HP339A, it could be a packaged oscillator source. That unit has the source and analyzer in one package. Some other units, maybe like the Tektronix units, don't have a dedicated source, but they're modular, and a lot of times you'll see those paired with the Tech SG505, which is a low distortion signal set. Keywords being low distortion signal source. You want a very good signal source for your distortion measurement. So we'll say, for example, we have a signal distortion source with a signal purity of 0.001%. That means that the harmonic content of this source, all of the harmonics of this source and noise are below 0.001%, or they're minus 100 dB down from the fundamental. Okay, so that's a pretty good source. And what that's going to do is that is going to contribute to our measurement floor. So say we have this low distortion source, and we have an ideal perfect distortion analyzer that has an infinite measurement floor. But when we put this low distortion source into that analyzer, the analyzer is then going to measure the floor, the distortion measurement floor, as 0.001%, because that's the limit of our signal source. Now, if we put a device in between that ideal distortion analyzer, and this is an ideal device that we put in between. So this ideal device has an infinitely low distortion floor. It has it makes no contributions to nonlinearities. It alters the test signal in no way. Then we're still going to only be able to measure down to 0.001%, because that's the floor of our signal source. So you kind of see here that when we start off with the distortion measurement, the better our signal source is, that's going to help set the limits for how low a distortion measurement we can make. Now, this may or may not be that consequential, depending on what you want to test. If your device under test is, say, a vacuum tube amplifier, which may have 0.5 or 1% or 3% distortion, then obviously you don't need this level of floor. You could probably get away with making a measurement with a source of, say, maybe only minus 80 dB or 0.01% distortion, because you're still well below the floor and your device is going to contribute that much more to the distortion. So you're not going to really need that extra room to the floor. However, if you're testing a really good device, then you would need a the lower distortion measurement of your signal source. Some things to think about: how good is my source compared to what I'm measuring or what I'm expecting to see on a measurement? And then you can say, well, I could use this source, or I can use this source, or in the case of a complete unit where you have a signal source that's built in, then you can know, okay, well, what's realistically a distortion level that I can measure? And you can sort of figure out, well, is the measurement I'm seeing, is this realistic, or is this a measurement that's limited by the system floor and I'm really not seeing the true performance of my device? All right, so we mentioned already we have some device under test, maybe an amplifier, maybe a preamp, whatever source you might be testing. That's going to take our input signal, and it's going to do something to that input signal. Depending on the performance of our device is going to determine what it does to that signal. But whatever it does to that signal, we're going to have an output from that device. The output of that device is going to go into our distortion analyzer. All right. So now the first thing that it does when it gets into our distortion analyzer is that signal is going to go through some sort of input system, whether that is an attenuator or an amplifier. It depends. What this input system is going to do is it's going to take whatever the signal level is at the input, and it's going to condition it down to a level that the analyzer can use for measurement. And what I mean by that is, say we've got a power amplifier as a device under test. The output of that power amplifier is going to be some large value, maybe 50 volts RMS or something. It depends on what your level of input signal, how much amplification is, but potentially there could be a large input signal. We need to take that large input signal and lower it down to a level that the analyzer can look at and not be damaged. Now, also, you could have a preamplifier here, or maybe you're testing some oscillator with a low signal output level. Well, in that case, we would need to amplify the input signal level to bring that level up to a level that the analyzer can measure. Either case, we've got an input system here on the front of our distortion analyzer. It's going to bring our input signal to a range that the analyzer can use. Once we've conditioned our input signal, next thing we'll do is we'll filter. So we're going to run our input signal through a filter. And what we need to do here is we're wanting to remove our test source so that all we have left is whatever harmonics that were produced by our device under test. So say our low distortion test source is at 1 kilohertz. It's a pretty standard frequency of measurement for audio applications. So we put our 1 kilohertz 0.001% low distortion source through our device under test. We're going to get on the output of the device under test, we'll get our 1 kilohertz test signal, and we may get some harmonic products. We'll probably get some second harmonic, some third harmonic, and so on. Because what happens is whatever non-linearities our device under test has, it's going to alter the shape of our test signal. And when our test signal is altered, that's going to produce harmonics. So now we've got our 1 kilohertz test signal, plus we've got some harmonic products. We'll condition those signals in our input device on the distortion analyzer, and then we're going to filter that test signal. So we're going to have a bunch of different signals coming in through this filter, and we want to remove our test source. So we want to get rid of our 1 kilohertz test signal. So that all we have coming out of our filter is harmonic components of the test signal. So we'll have some second harmonics, third harmonics, fourth harmonics, and so on. So how do we do this? Well, typically this is done with a notch filter. And you'll remember from the previous video we talked about the filtering. This is the HP334A service manual. We talked about this graphic here. And we looked at the notch filter and how that works with harmonics. So in the case of the HP334A, they use a Weinbridge notch filter to notch out the test source. And what we see here on the graph is at our fundamental frequency here, we have a very deep notch. And what that's going to do is say if our fundamental frequency is 1 kilohertz, when we pass a 1 kilohertz signal through this notch filter, it's going to have a heavy rejection at 1 kilohertz, which means it's going to take whatever components of that signal at the 1 kilohertz frequency, and it's going to attenuate those heavily. So that 1 kilohertz component is going to essentially go away, or be, it's not going to go away, but it's going to be reduced significantly compared to the other signals. And that's going to leave second harmonics and third harmonic components and so on. But as we see here with our notch filter, it has it's got a very deep notch at the tuned frequency. But it also affects our second and third harmonics and so on. As you can see from the second harmonic here, our normal signal level being up here, our second harmonic is attenuated quite a bit. This is about minus 7 dB or so of reduction. Our third harmonic's got some attenuation here, fourth and so on, really till we get almost to the 10th harmonic before we start getting back to our normal signal levels. Well, this isn't good because if we have some second harmonic content produced by our device under test, that second harmonic content is going to be attenuated, and it's not going to be counted correctly when we go to make our distortion measurement. So therefore, our distortion measurement's not going to reflect the actual distortion levels, because the distortion products that we're measuring, the second and third and fourth and so on harmonics, are going to be attenuated. So how do we adjust for the attenuation of those harmonics? Well, we use feedback in our notch filter. And that's what this dotted line shows here. So when we apply the appropriate levels of feedback to our notch filter system, what happens is we tighten this notch and we make it very, very narrow to the point where our second and third and fourth and so on harmonics are not affected, or are not affected significantly enough to alter our measurement. And this is where we get into our measurement, start to find our measurement errors of our system. The tighter we can make this notch, the less we affect our harmonic content, the greater amount of accuracy we have in our distortion measurement. We reduce the errors of our distortion measurement set. So we want to have our notch filter, and we want to have significant enough feedback from our notch filter to tighten that notch so that we can minimize measurement errors and get a more accurate measurement of distortion levels. Now, the way we just mentioned that on the HP334A, they use a Weinbridge. In some of the later instruments, like the HP339A, they use I believe it's a bridge T. Many of the instruments used twin Ts, different types of notch filters. And those can vary from system to system. And they have varying complexities as far as tuning. This is probably the most complex part of your distortion analyzer system, is getting the notch filter system to work and the tuning of it, because it requires a great deal of switching, especially when you're talking about covering wide frequency ranges. The HP339A distortion measurement set has a great deal of switching involved. The HP334A uses a large tuning capacitor and a resistive network to do the tuning on the bridge. So it takes quite a bit of switching and complexity to get that bridge to tune, to get those notch filters to tune over the wide range that you're looking at for your different analyzer sets. So as we shift the level, we need to correct for that level. And the way we do that is we have some sort of level control system at the output of our notch filter. And the way that this is in the more modern instruments like the HP339A, this would be called your auto set level. Now, in the case of the HP334A, this is done manually, but this is going to be a level control system. And what it's going to do is it's going to be looking back at the input level, determining what our input level is, and then at the output of the notch filter, it's going to be adjusting the level of the signal going through the auto set level system to essentially compensate for any level changes that were done by the input system. So it's going to take our input level at the distortion analyzer and it's going to normalize our signal levels coming out of the notch filter to a level they would be at the same level at the input of our system. All right, so now we've got our second harmonics, third harmonics, and so on, fourth harmonics, and they're coming out of the auto set level system and they've been level corrected to the correct level. So that now if we have a second harmonic component of, say, our second harmonic, say, is maybe at a level of minus 70 dB at the input, we've done our input level adjustments, we've done our filtering, and our auto set level is going to correct that so that our second harmonic component that was at minus 70 dB with respect to the carrier source is now corrected to the correct level. So it's going to be minus 70 dB at the output of the auto set level. And so on. It's going to do that for all of the components coming out. So now we've got our signal coming out. The last thing we need to do before we take our measurement is we're going to apply some filtering. Now we've got more filtering. Now this isn't like the notch filter. What we're going to do here is this is where we'll have our various filters that we can select. On the HP334A unit, there's not a lot of filtering options. There's one high-pass filter that can be switched in that will attenuate products below 1 kilohertz. Now on the HP339A and some of the other later units like the Tektronix units and the Kronheit units, there's a couple of filtering options. And we'll go with the HP339A as an example. We have a 400 hertz high-pass filter. We have a 30 kilohertz low-pass, and we have an 80 kilohertz low-pass filter. And these are all selectable filters that can be implemented or removed as desired. And this would be depending on what type of measurement you're making. If you're making a measurement at, say, 1 kilohertz, which is what we selected here from the start, then we would probably apply the 400 hertz high pass. That way we could remove any noise or power line components, things that aren't related to our signal, but signals that can creep into our measurement system through radiated noise or maybe some ground loop issues in our setup, whatever kind of noises and we wouldn't want to attribute those signals specifically to our measurement because they may not be present in all cases. Say we're doing production line testing, the noise in a production lab may be different than noise at the end user's home. So we don't want to attribute those noises that may be due to our setup and say blanketly that they are always applicable, because they're not. So we may use a 400 hertz high pass filter to remove the power line noises. or setup noise. Again, if we're using 1 kilohertz, we may also choose to apply the 30 or 80 kilohertz low-pass filters. That's going to limit our noise, our high-frequency noise that's maybe present in the system, but it's not due to our device under test. An example may be our signal source. Say we're using a signal source from an arbitrary waveform generator or some digitally generated signal source that may have a lot of high frequency digital noise in it that our device under test may not see because maybe it's outside of the range of operation of that device, but yet it's still being passed through the system. Say you're testing an audio amplifier and you got a whole lot, and maybe you have some digital noise at, maybe like 100 kilohertz or 120 kilohertz, something like that. You're wanting to test the audio range is 20 hertz to 20 kilohertz. Well, 100 kilohertz frequency is certainly not audible, and it's probably not going to be within the frequency range that anyone is going to be using for an audio system. Maybe you want to eliminate that to see if if your measurement results are due to high frequency noise, or maybe they might be due to something at a lower frequency. So we can use those different filters to sort of expand our understanding of the measurement. We can see how switching in those filters may affect our measurement, and then we can use that information to draw some conclusions about the measurement. Now, I noticed on a lot of different distortion analyzers, these are pretty common filter values. The 400 hertz high pass, 30 kilohertz, and 80 kilohertz low pass. And just a little bit of reading, I think some of these, in particular the 30 kilohertz, may have been dictated by the broadcast industry for making broadcast distortion measurements. I believe it has something to do with in the FM broadcast, your bandwidth is limited to 15 kilohertz, so they use a 30 kilohertz low pass filter to sort of set a measurement specification for broadcast. And like I said, these are pretty common values. The 80 kilohertz low pass filter would be used for doing something more like your audio testing or at a little bit of a higher frequency. There is a drawback to these filters in that they do alter the level of our harmonics. So if we're making a measurement that's close to especially the top of the audio range, maybe at 15 or 20 kilohertz, we may want to reconsider using these especially the low pass filters, because they would give us an invalid distortion measurement in that they would positively alter the results. Let's say we're making a measurement at 15 kilohertz, our second harmonic is 30 kilohertz. Well, if we're attenuating our second harmonic at 30 kilohertz, then we're going to get a better response, but we're going to get a better response on distortion measurement because we're attenuating components that we need to otherwise quantify. So always take into consideration when you're using any kind of output filtering how that might adversely affect the accuracy of your measurement. All right, going from our output filters, now we finally get to the quantization of our measurement. And so how do we do that? So we've got a bunch of different signal components. We've got, so if we have 1 kilohertz test signal going in, we would have maybe some 2 kilohertz components, some 3 kilohertz components, some 4 kilohertz components, maybe some high frequency noise, maybe some low level power line noise. We have a bunch of signals, and we've got just random system noise throughout the system. And that all needs to be quantified. So we take all of those components and we're going to add all those components together. And that's where we come to our converter. Now, the more modern instruments, there's two ways that this is done in distortion analyzers. Some of the more modern units like the HP339A, like the Tektronix units, will use an RMS, a true RMS to DC converter. And this is probably the more accurate way of doing this measurement. What this is going to do is this is going to take whatever AC components, it's going to add them all together and convert them to a DC value. Then that DC value can be displayed on a panel meter. Now, the RMS DC converter is more accurate, but it's also more complex in that this is done through the use of specialized integrated circuits. So these integrated circuits, namely the AD536. This IC is used by the HP339A. It's used by the Tech AA501. It's used by the 4804 instrument. And it's probably used in other ones. Those are the ones that I can remember off the top of my head. This Analog Devices 536 is a dedicated RMS to DC converter chip. It's a very good chip. It has a very wide response window. Don't have the data sheet in front of me, but depending on input signal level, you can take it's useful out to I think close to 1 megahertz or higher for RMS to DC converter applications. So there's a very wide range of response. Another very good AD chip for RMS to DC conversion is the AD637. Now, I haven't seen this IC used in any of the, I guess, the more modern or more established distortion measurement sets. But this chip has an even wider frequency response, and I believe the data sheet advertises out to 8 megahertz. So very, very wide response on this RMS to DC converter. But these chips are expensive. This AD536 will run you about $70 for one package from distributors like Mauser and whatnot. The AD637, I believe, is a little bit cheaper, but it's still a very expensive chip. Now, if you look at the 339A service manual, what you'll find is this chip isn't there. It's an HP branded chip, but if you look at the service manual, you do a comparison, a pin-to-pin comparison of the AD536, you'll find that it's the same chip. It's just been rebranded by HP, probably for proprietary or anti-cloning measures. Now, so we mentioned one method. This is one method. The other method is to use an RMS, a active rectifier that is calibrated for sine wave response. Now this is how some of the older instruments like the HP 334A use, and I believe the Kronheit instrument one of them uses this. The Kronheit instrument that I looked at, and I don't remember the number off the top of my head, but it had it did not use the AD536. They may have actually done the RMS to DC conversion portion. They may have actually built that out of discrete components. I'd have to look back at that again, but I know that the 334A unit does active rectification. Also, the older variants, the 331, 332, 333, those units also use active rectification. Now, the active rectification can be fairly good. It's a little bit less accurate than a true RMS to DC converter. And specifically because when we talk about taking the measurements here, typically these active rectifiers are calibrated for sine wave response, meaning that you'll only get a true response if you have a true sine wave going into the rectifier. You have a true sine wave going into your active rectifier, you'll get a true conversion to DC at the output of your meter. But if your input signal is anything other than a true sine wave, it's going to alter what comes out of the output of the active rectifier, and that's going to result in measurement errors. Now, what we've got coming out of our distortion products typically are not going to be pure sine waves. In fact, they almost never are going to be pure sine waves. They're going to be some harmonic components that may or may not be pure sine waves, and they're going to have noise and whatnot with them. So all of those things added together are going to alter the accuracy of our measurement. And this is talked about in the HP 339A service manual, where they do some comparisons between true RMS and using active rectification for the signal measurement. And they talk about how you could have some error. And the error is variable. It depends on, like I said, what type of signal and what type of waveform you have going in. But typically it can result in maybe a few dB of difference between RMS DC and active rectification. And the way that is manifest is it shows a lower than actual response. So say we have a reading at our output meter here showing a distortion of, let's see, our distortion maybe says our distortion level is maybe 0.03% here when we measure with the true RMS to DC converter. Maybe our active rectification result shows a distortion measurements of maybe 0.28%. So it looks like it's a little better of a number. But what we have to keep in mind is that with active rectification, our signal response is going to show a little bit better than the true RMS value. And again, that's because of our signal response from the active rectification responding to a signal that's less than a perfect sine wave. It's going to produce an output that's less than what's actually going into it, because we're not doing the true RMS conversion. We're not taking all of the power of that system and converting it to DC. We're taking some of the power and converting it to DC, and we're losing some of it because of the fact that it's calibrated for a particular wave shape, and we're not getting that wave shape going in. So it's something to be aware of when you're looking at distortion analyzers. You're looking at what type of metering circuit they use, whether they use true RMS or whether they use active rectification. Those things can play into your measurement results. So here we go. We've essentially built on paper a complete distortion analyzer system from our signal, our test signal, through our device under test. We've got an input system to adjust our input signal level to a level that the analyzer can use. Then we notch out our fundamental test signal. We have our harmonic content coming out of our notch filter, which is tightened by the use of feedback to only eliminate the fundamental and not eliminate or alter the harmonic content. We readjust that output to correct for level variations in the system so that the level of our harmonic components is the same here as it is at the input. Then we apply any filtering, and then we finally use some summation to add all of those components together and come up with a distortion measurement. Now, two more things to talk about here for distortion measurements. We talk about total harmonic distortion, and we talk about total harmonic distortion plus noise. So these are two different measurements, and sometimes I may use these interchangeably, but they're not the same. Technically, they're not the same. They're different. Total harmonic distortion is when we look at the harmonic content of a signal. This will be something that we would do with a spectrum analyzer, where we might look at a signal on a spectrum analyzer and we might see the levels of our harmonics. We look at a 1 kilohertz signal on a spectrum analyzer and we would see if our 1 kilohertz signal level is normalized to some 0 dB value. And then we would look at our second harmonic content, which may be at a level of minus 60 dB below our fundamental. And then we might look at our 3 kilohertz harmonic component, which may be at some level of, say, maybe 70 dB. We could add those second and third harmonics together and come up with a value of harmonic distortion being relative to our fundamental. We do add those numbers together to come up with some value, say arbitrarily set minus 75 dB. I know that's not correct, but just for the example here, then we would say that the sum of our harmonic components is minus 75 dB below the fundamental. That will be a measurement of total harmonic distortion. We're looking at the distortion with respect to harmonic components. When we do total harmonic distortion plus noise, we then take the level of our harmonic components and we add the signal level due to noise. Now, this is something that you could not do with a spectrum analyzer because the noise level changes continuously. So we could look at a signal on a spectrum analyzer and we could see noise on the spectrum analyzer. But that noise level is only shown, the noise level shown is only applicable for that one sweep of a signal, meaning that as the spectrum analyzer sweeps the signal, the noise level is changing continuously. And so that measurement, the harmonic distortion plus the signal due to noise, is changing continuously. This is an instance where you would need a measurement that is being performed continuously over and over again and updating in real time. This will be something that you would see on an analog meter. And this is something that will be measured by using a distortion analyzer. The distortion analyzer is continuously taking all of the data, all of the levels of the harmonics, all of the levels of the noise, and it's continuously summing all of that information and displaying an output on a meter. So when we talk about taking distortion measurements, total harmonic distortion, very easily done with a spectrum analyzer. Total harmonic distortion plus noise, that's where we're looking at a distortion analyzer, because that's going to continuously take all of that information plus noise and add it together and give us an indication of total harmonic distortion plus noise. All right, I hope that this has been a little bit sort of a good refresher on how all of these systems work. And what I'm going to do now is I'm going to move the camera, we'll get some equipment set up, and we'll sort of walk through how this is done. And we'll look at some of these concepts that we just talked about, looking at the spectrum analyzer and looking at a RMS voltmeter, and we'll see how the differences between total harmonic distortion and total harmonic distortion plus noise. And then from there, I hope that we've got some of these concepts down. I hope that I've relayed the information to you in a way that sort of makes sense, and I hope it's correct. But I don't claim to be an expert. This is just things that I have observed in my looking at the way all of these systems sort of work. All right, let's get some equipment set up and we'll go from there. All right, let's have a look at our setup here. Now, we've got some fan noise, so I've got the spectrum analyzer turned on, but we'll just have to deal with that. All right, so let's talk about our setup. What we've got is our function generator coming in here. This is producing two signals. I've got a signal on channel 1 at 1 kilohertz, and I've got a signal on channel 2 at 2 kilohertz. Both of these signals are at 1 volt RMS. We've got 1 kilohertz, and channel 2 is at 2 kilohertz at 1 volt RMS. Both sine waves. I've got channel 1 going into a mixer box here on channel 1, where I can vary the input level here with the potentiometer, which is currently set for maximum level, and the output here at this B and C. Channel 2 is going to go through this attenuator box, and that's going to let me vary the attenuator, vary the level of our channel 2 signal in steps. I can go in 10 10 dB steps for the demonstration of measuring harmonics with a spectrum analyzer. The output of the attenuator goes into channel 2 of this mixer box, with the potentiometer also set for a maximum signal level, and these two signals are mixed here at the output of this box. So this output here is a mixed combination of channel 1 and channel 2. And I haven't taken this apart, but what this is there's a buffer amplifier in each of these, and then they're mixed with a summing amplifier so that the two will minimize interactions with each other. This signal comes out and goes to the spectrum analyzer. I've also got this signal here is also present at this BNC here, which is going to the oscilloscope, so we can see our signal on the oscilloscope. Now we'll take a look at the spectrum analyzer. We see that we have our fundamental here at 1 kilohertz, and that's showing a value of plus 12.6 dB. And if we look at our fundamental, our reference being here at the top of the spectrum analyzer, we can see that our second signal is right here, sitting just below that at minus 20 dB. So if you look at, you can do the math and you can add those two harmonics together. Just looking at total harmonic distortion, we can come up with a value that equates to 10%. So this is a 10% harmonic distortion reading. And that's just based on summation of the two harmonic components, not including the noise of the signal. Now we look at the noise. The noise is very, very far down on this. So we're at our noise level is at minus, we'll call it minus 80 dB. There may be a couple of peaks that are a little bit higher, but we'll just call it, for easy math, we'll call it 80 dB. So if we were to do a sum all of this together, we've got a signal level at 0 dB, we have a harmonic at minus 20 dB, and we have a noise level at minus 80 dB. If we were to put that in a harmonic distortion measurement set, we're going to come up with 10% total harmonic distortion plus noise, because the noise level is so much lower than our harmonic component that it's going to affect the measurement, but it's not going to affect the measurement in a really significant way. So let's put that in the distortion measurement set now. I'll use my HP339A, and we'll take a total harmonic distortion plus noise to see what the difference in measurement is. All right, so we've tuned the HP339A to 1 kilohertz. We're looking at the minus 20 dB range, and we see that our measurement is pretty much right on at showing a full range of minus 20. So 0, this point here being the minus 20, and we're actually looking at about a minus 20.2 dB. So a little bit, about 0.2 dB off of the spectrum analyzer. I would say that's due to just differences between the systems. And I can tweak that on the mix box to make it exactly minus 20 dB, but we're not going to do that just to keep the signal the same. So we see that, as stated just a minute ago, that taking this measurement with the harmonics so far apart and the noise floor so much lower, that the noise floor doesn't really alter the measurement in a significant way. Now what we can also do is we could apply a filter. So we can put our 400 hertz high pass filter in there, and we can see how that responds. The needle changed a little bit, but not a whole lot. Let's take that out, and we'll put in our higher filters. We can see again that we did change. And when I'm pressing these switches, what actually is happening internally is the signal path is interrupted momentarily during the push of the switch. That's why you see the needle sort of bounce as it does when we do this. We can put in the 80 kilohertz, not much change. So we know from that measurement that there's not a lot of line noise present in our system, and there's also not a lot of high frequency noise present in our system, because we're not, by applying these filters, we're not having any meaningful change to our measurement. So we can say in this case that that is the measurement of our system. We're looking at 10%, a 10% total harmonic distortion waveform with total harmonic distortion plus noise being pretty much the same measurement. All right, so looking at the waveform on the oscilloscope, we can see that we have a sine wave, and you know, for the untrained eye, it looks like a pretty good sine wave. But if you see, it's very slightly leaning to one side. You notice that this slope here is a little bit steeper than this side here, and that's the effect of the waveforms being added together. I can back the distortion out, so now we're at minus 10 dB, so this would be equivalent to a 30% distortion level, and you can see now the sine wave is greatly distorted. Now, to the trained eye, some can claim that they can see on an oscilloscope distortion levels at 1% or even 0.5%. So let's see if we can see the difference. Now, this is 10% distortion here. If we back it down another 10 dB, now we're looking at 3% distortion level. That's starting to look like a pretty good sine wave. If we take it down another 10 dB, this is 1% distortion. Now, you tell me if you can see that on an oscilloscope. I don't think I could see that on an oscilloscope. Here we go at minus 50 dB. This is down to 0.3% distortion, and we see that there's really no change there from that point on, and you're not going to see anything else because the change in the sine wave is so small compared to that distortion product that we're adding in that you really can't see that much change. All right, back to our 10% sine wave. So now let's look at a signal with a much lower distortion level. This right now is a signal at minus 80 dB, and you can see from the spectrum analyzer that the second harmonic is just barely visible there within the noise of the system. In fact, if we didn't know where the harmonic was at all, or that the harmonic was there, we may not even see it when we see other spurious signals like this one at 2.492 hertz. So this may just look like some random noise to you, but this is in fact the harmonic. Now we can see that our harmonic is now inside the noise of our measurement. There it is there, we're at minus 81 updated there, and even lower still down here into the noise. This is an instance where you really need, if you wanted to find the harmonic content of a signal, especially a signal like this where you have much greater spectral purity, you really need some sort of distortion measurement system or a notch filter or something, so that you could isolate this this large fundamental here and increase the dynamic range of the spectrum analyzer. And that's what we did in the previous video with the notch filter, is we used that notch filter to remove the fundamental, and then we could focus in on the lower signal levels of the harmonics. And that's what a distortion analyzer does. Distortion analyzer is going to remove this large fundamental signal so that it can zoom in and really find these low-level harmonic components and the noise. So let's look at this now on the distortion measurement set. Now looking at the signal on the HP339, and we can downrange. As we see now, we're starting to come on scale. We're at minus 60 dB on the range. and there is our signal. So we can see that we're just now on the lowest range of our measurement. We don't have any of the filters in right now, and we're just now at the 80 minus 80 dB. So that is our measurement. Our total harmonic distortion plus noise is there. Now let's see what we can do about the noise level. If we take out some noise, does that lower our measurement? See, now we've actually had a little bit of a noticeable change there, whereas we were right here just barely in the range. Now we've gained about 0.2 dB of measurement there, removing noise. We can go further and remove some more noise, some of the higher frequency components, and we see now we've had even more of a change now, almost at 1.5 dB of signal. And what we've done, now remember that we're measuring a signal at 1 kilohertz, and we've put in a low pass filter at 80 kilohertz. So this effectively is removing components out to the 80th harmonic. We don't really necessarily are concerned with components that high out, because they're so far out that they're going to be so insignificant from the signal, because as the harmonics go from a signal, they tend to be smaller and smaller in magnitude. So any harmonic, an 80th harmonic of 1 kilohertz, is going to be so small that it's not going to be contributing to a meaningful measurement, even with the filter, when the filter's not there. So anything that we remove by placing this filter in is going to be signal levels that are high enough that are due to noise. We can bring that range in even further and go to 30 kilohertz. Even 30 kilohertz, we're talking about the 30th harmonic of 1 kilohertz. Again, we picked up some more. We took out some more noise, and we've got an even greater measurement there, sitting at minus 83 dB now, almost on our measurement. So you can see how the filters can affect our signal measurement, and we can use those filters, and based on what we know about our test signal, we can decide whether this filter is appropriate or whether it's not appropriate. In this case, I would say the 30 kilohertz low pass filter for a 1 kilohertz test signal would be appropriate. But if you wanted to be conservative on your measurement, you could certainly apply the 80 kilohertz low pass filter and say, well, that's well within any kind of measurement conservatism there. But we see that the difference there between taking the measurements with a spectrum analyzer versus taking the measurements with a distortion measurement system such as the HP339A. So I hope that you've enjoyed this video. I hope it's been helpful for you. I am trying to cover some of the concepts here as we go forward in this series. Talking about distortion analyzers, talking about signal sources, and how the two play in together to make a distortion measurement set, both of our source and our analyzer. Our measurement floor is ultimately going to be limited to the performance of our measurement system. We have a better source. We can take a better measurement, a lower measurement. If we have an analyzer that can, the more an analyzer can reject the fundamental source, and the less it contributes to overall system noise and overall harmonic distortion, nonlinearities, the lower our measurement floor is, the lower of a measurement we can make. Of course, we're going to be limited to whatever the performance of our device under test is. So all of these things are going to play into our distortion measurement, and how low a measurement we can make and how accurate a measurement we can make based on the type of metering we use. So I'm going to wrap this video up. This is, like I said, part one. Part two, we'll get into my project that I'll be presenting here. Like I said, I've been doing on this project for over 2 years now, so I'm ready to move on with this project. I'm ready to present what I have, and hopefully you can take something from that. In case you haven't figured out what that project is now, it is a distortion measurement set. I found a very good article on the internet. It's an older article by a man named Robert Cordell that produced in a magazine publication, audio magazine, back in 1981, a project for the home builder to construct a complete distortion measurement set with both a test source and measurement analyzer system in one package. And I have completed that project, and I would like to present that to you for information. There's quite a bit of following on this project on the internet, so I'm sure for most of you this is nothing new. But what I found in my research is that there's not a lot of detail. There's a lot of detail in the original article, but there's not a lot of detail by other constructors out there. And of course, with any type of thing like this, the more information out in the community on various build techniques, findings as you're constructing a project like this, of course, it just adds to the available information. It helps everybody out there, or anybody who might want to take on this project. It was a very in-depth project, a very complex project, and very expensive project. I spent quite a deal of resource putting this together. Again, it wasn't about so much of a cost issue. To me, it was more of a personal challenge, something for me to take on and see what I could do with my skills and where I could learn. And I think I've learned a lot and had a lot of improvements in my construction skill. So I'll be looking forward to presenting that to you in part 2, and we will see you all there in that video. Thank you for watching.